Now this session I'm experimenting again. I've moved back to the living room from the bedroom, and last time one of the reasons for moving was the light up here was too bright for my eyes. My eyes were seriously starting to hurt. So what I've done this time, I've taken out like up there were 3 bulbs, light bulbs, so now there's only 1, and so the lighting is less. So I'm hoping this comes out okay, and because it gets darker and darker as you head this direction. So I hope, but of course now I'm filming in high definition, so I hope it's not a problem. I hope the camera can adapt to the lighting level without too much of a cost to the definition. So I hope it stays clear. Well, but yeah, we'll see. Alright. Okay, so like I was saying in the previous session, you switch on the magnetic field, and the energy will shift, a change, delta, a change in the energy by this amount. Now, what's this? Haven't seen that before. Well, it's in a sense the magnetic moment, but it's defined, 3 bars, it's defined this way: E h bar over 2 me. E is the charge on the electron, this is the mass of the electron, and this term was made famous by Bohr, this Niels Bohr. So it was just simply called the Bohr, I've left out an N here, the Bohr magneton. Bohr magneton. Okay. So now because your M can range over 2L plus 1 levels, as I was saying earlier, this energy level here before the B gets switched on is in effect, in terms of M, is 2L plus 1 degenerate. So alright. Now the electron, when you have a particle, say a classical particle whizzing around in an orbit, let's say, it'll have a magnetic moment due to its motion, due to its orbital angular momentum. Now the electron has a kind of intrinsic, within itself, whatever that means. People talk about electrons being point particles. Anyway, so the electron has a kind of intrinsic magnetic moment because of its spin. Now, Dirac, I've got books here, I'll talk about this a bit later, but at graduate level, first year master level, we will spend a lot of time, a whole course, on relativistic quantum mechanics. It's quite an advanced course, and most of that is dominated by Dirac's equation. It's sort of the Schrödinger equation equivalent for relativity, the relativistic case, when your electrons, for example, are at moving at very high speed, so you get relativistic effects. The mass goes up because it's getting close to the speed of light in terms of speed, stuff like that. So Dirac, as saying in earlier sessions, Dirac merged quantum mechanics with relativity, special relativity. Okay. Now, out of that, coming out of this theory, and we'll do it at M1 level, he got a magneton, in a sense, with this value, where S is the spin. Now, oddly, the orbital magnetic moment, say like classically, you've got a 2 under here. I don't think you can see it, but the classical formula, you'll have minus E over 2 me, and you'll have an L here for the orbital angular momentum. But this is now the spin, and there's a missing 2 here. Well, it's not missing. It just, but it's just different. The relativistic treatment of Dirac predicts this term here without the 2, which is odd. So it's different. By a factor of 2, it's twice as large as the orbital magnetic moment, right? So with this term, with the spin, then you switch on. Now this electron then will have a kind of magnetic moment. So how do you visualize that? Maybe some kind of charge flow within the electron. Such analogies are dangerous. All right. So there'll be, in other words, the electron, due to its spin, has a kind of, well, a magnetic moment. Right? So you switch on the magnetic field, and you'll get an energy shift, similar to this, right? But it's double it. It'll be double the Bohr. So it'll be there's a 2 here due to now m ranges. Now there's only 2 states, right? And remember, m ranges from -L to L in steps of 1. Now the m for spin is just h bar over 2 and minus h bar over 2, multiples of h. So your change in the energy will be this, which is equivalent to this. But m now, there's no m here. But you've got this 2 due to the 2 missing here from Dirac's theory. Alright, well that's pretty well the end of this, not just this session. It's the end of the chapter. It's been a long one, 20 pages. It's the second longest chapter in the book. And I still have a square left, so I'll turn around. And so I just finished off filling in a bit of space, basically. So the next chapter, chapter 8, we'll be dealing with central potentials. For example, talking about the hydrogen atom, where the potential is generated by the charge on the proton, which is the nucleus of a hydrogen atom, right? The nucleus of a hydrogen atom is the simplest. It's just one nucleon, which is one proton. And it's effectively at one point, so the potential generated by that proton, by that nucleus, is effectively central. It just comes from one center, from one place, one point, right? And when we do the quantum mechanics of that, it allows us to examine the quantum mechanics of the hydrogen atom. We've done it a bit already, but we restricted ourselves, if you remember, to effectively Hamiltonians that had only the position, the spatial side. We neglected the polar angles, the orientation, the theta phi side of the Hamiltonian. But now that we've done angular momentum, we can go back and do the quantum mechanics of the hydrogen atom in more detail. We can deal not just with the space